Hi, in this video we're going to look at some expected values in a multivariate case. So let's get right to the examples. Got a lot to do here. Let's get to the example. Suppose that we have this joint distribution given to me in this table form. So let's first look at what the marginal probabilities would be for this joint distribution. So just add up the rows and the columns of probabilities, get the marginal probabilities. Notice that all those probabilities, the marginal probabilities add up to 1, so I've done my arithmetic right. And then the marginal probabilities give rise to the marginal distributions. This way, we've talked about this in previous video. So those marginal probabilities define the marginal distribution. And then I can take expected values of each of these marginal distributions for cap x and cap y, and I get these values 1.1 and 1.07 respectively. Notice I could also take other moments with respect to these marginal distributions. For example, the second moment of the cap x random variable, I would square the values in cap x and then take the sum product. And I'd get a 2.07 number for that. And I could also take the second moment for the cap y random variable by squaring the values of cap y before I take the sum product, and I'll get a 1.71 number for that. So now that I have the first and second moments, I could even get the variances then for this marginal distribution. The variance of cap x is what's this, 0.8379. Second moment minus the square of the first moment, and likewise the variance of cap y is still second moment minus the square of the first moment for cap y, and I get the 0.5651 number. Oh, I got ahead of myself. I'm sorry. And so those are that's going to come back later on in the video. I wanted to get these marginal parameters, the expectation and the variance for the marginal distribution, so I'll come back to that. Okay, so now let's go back to our original table. I could look at other types of random variables. For instance, I could look at what the sum of cap x plus cap y would be. So all you do here is it's all discrete here. So you just take the support of cap x, which is 0, 1, 2, and 3, and the support of cap y is 0, 1, and 2. And for each one of those situations, you just add up the values. For instance, when they're both 0, I get a sum of 0, and that occurs with this probability. It's in red, the 0.12. If I want to get the next smallest value that cap x plus cap y could be would be a 1. So notice that could occur in two different ways, though. That could occur by cap x being a 0 and cap y being a 1, and that probability that cap x is 0 and cap y is 1 is the 0.13 in red. Or I could have had the cap x be 1 and the cap y be 0, and the probability of that occurring would be the probability in green, the 0.08. So the probability that cap x plus cap y would be 1 would just be the sum of those two probabilities, or 0.19. Likewise, I could have a value of 2 for the sum of cap x plus cap y, and there were three ways for that to happen. Cap x could be 0 with cap y being 2, cap x could be 1 and cap y could be 1, or cap x could be 2 and cap y could be 0. And so add up those corresponding probabilities, those colored probabilities that I have in the table there, and you'll get a 0.25 for that. The next smallest value for cap x plus cap y, I could get a 3. And again, just kind of go through the process that we've already talked about. You'll get a probability of 0.29 there. Or I could get a 4 for cap x plus cap y with a probability of 0.13. Or I could get the largest value I could get for cap x plus cap y would be a 5, because cap x can be at most 3 and cap y can be at most 2. And then the probability of that occurring is the 0.02. Notice that the sum of all these probabilities is 1, so I haven't left anything out. And then if I wanted to know the expected value of cap x plus cap y, I would just take the sum product, and you'll get a 2.18 when you take the sum product of the columns that are in red there. Notice I could also take the second moment of the sum cap x plus cap y. In other words, I'm saying I take the expected value of the square of cap x plus cap y. I've got the cap x plus cap y values, so now I just square them and then take the sum product. I find it useful to add a column to the table here, so I'm going to append a column to the table where I have the square of the values of the random variable, and I'll leave it to you to show that I did the arithmetic right here. And then I'm going to take the sum product here to get the expected value then, or the second moment of cap x plus cap y, and I'll leave it to you to show that you get a 6.38 when you do that. So then I have the first moment and the second moment of the random variable that is cap x plus cap y. So I could take the variance of cap x plus cap y. And I take this, again, just take the second moment minus the square of the first moment. You'll see, again, I'll leave it to you to show the arithmetic. We'll give you a 1.62, what's that, 1.6276. Okay, so I want to make some comparison now with the parameters that we evaluated before with the marginal distributions of cap x and cap y. So let me remind you of what those are. So first of all, notice that the expectation of cap x plus cap y, the 2.18, that actually is equal to the expectation of cap x plus the expectation of cap y. And I knew that that was going to happen anyway because I know that from previous videos, the expectation is a linear operator. So I could just, the expectation of a sum is just the sum of the expected values. I knew that. But notice the variance is, the variance of cap x plus cap y in this case is not equal to the variance of cap x plus the variance of cap y. And so again, this just reinforces the fact that I've talked about before, that the variance is not a linear operator. So again, we'll come back to that in a later video. We'll come back to that statement again. Now, I could look at more complicated instead of just a cap x plus cap y. Maybe I have like, and I'm just making something up here, maybe I have something like a 3 times cap x plus 7 times cap y, and I wanted the expected value of that. Well, again, you just kind of go through, it's all discrete, so you just look at the possible values of the random variable cap x and the possible values of the random variable cap y. Look at all the arrangements, go through and calculate what the sum of 3 times cap x plus 7 times cap y would be, and look at the associated probability for that sum. For instance, if they're both 0, you'll get a sum of 0, and that probability would be 0.12. There's a bunch of stuff that I'm leaving off here, but if we could look at the situation where cap x is 3 and cap y is 1, then 3 times 3 is 9, 7 times 1 is 7, so 9 plus 7 is 16. I'd get a value of 16 for the 3 times cap x plus 7 times cap y, and that would occur with probability 0.03. And I just go through and you could fill out the entire table this way. And then to take the expected value, I would take I'm sorry, let's see. Yeah, so then to take the expected value, I would take the sum product of those values in the table. And when I do that, I got a little ahead of myself on my. I could take the sum product of the values in the table. I didn't give you all the values in the table, so I can't actually give you a numeric value there. I got ahead of myself on the slideshow there. The easier way to do this is to use the fact that I have the expected value of cap x and the expected value of cap y already, and use the fact that I have a linear operator. So the expected value of the 3 times cap x plus 7 times cap y, using the properties of a linear operator, it would be 3 times the expected value of cap x plus 7 times the expected value of cap y, and going through the arithmetic, I get a 10.82. So that's much easier to do than actually filling out the values in the table. Just use the properties of a linear operator. Let's talk about another expression that we could take the expected value of that's going to be show up quite a bit in the next few videos. And that is if we take the product of cap x and cap y. Now I have a dot there in the table. I have a dot between the cap x and the cap y, so to represent I'm taking a product. But from here on out, I'm just going to leave out the dot that's implying that it's multiplication, and just write the cap x and the cap y next to each other, and implied by that is that we're multiplying cap x and cap y. So again, I'm going to go through the process the same way. I look at the possible values of cap x and the values of cap y, and I just one by one go through and calculate what the product would be under those different situations. So for instance, when either cap x is 0 or cap y is 0, you're going to get a product of 0. So the value of cap x times cap y will be a 0, with probability being the sum of all those probabilities in red, because each one of those probabilities is corresponding to a situation where the product is 0. And if you add up all those probabilities, you get a 0.43. The next smallest value that the product could be would be a 1, and that would happen when exactly x is 1 and y is 1, and so I'd get a 1 as a value in the support of cap x times cap y, and with the probability of 0.15. The next smallest value I could get would be a 2, but notice there are two different situations that would give me a 2. I could have a cap x be a 1, a cap y be a 2, or a cap x be a 2 and a cap y be 1. And then those colored probabilities in the table are corresponding to those the probabilities of those events, and those are, I would add up those probabilities to get a total probability of 0.27 as the probability that cap x y is equal to 2. Likewise, go through the process. Cap x y could be a 3. The product could be a 3 with probability 0.03. It could be a 4 with probability 0.1. And the largest value that cap x y could be would be a 6, and that's when x is 3 and y is 2. It comes with probability of 0.02. I didn't put in here, I should have, but I didn't put in here that the sum of the probabilities is 1, so I didn't leave anything out. And now if I wanted to say the expected value of this product, then I take the sum product there and I get a 1.3. Again, let me put in the additional information on the marginal distributions, and I want to make the observation that the expectation of the product is not equal to the product of the expectation. So it's not a property of linear operators. Linear operators would say that the expectation of a sum is the sum of the expected values, but the expectation of product is not generally going to be the product of the expected values. Let's look at one more example of an expected value. One more example here that I've seen in the sample questions, and that would be, what if I had something like, what if I was seeking the value of the variance of a conditional distribution of cap x given that cap y is equal to 0? So I look at, again, I'm going to look at the distribution table for cap x given that cap y is equal to 0. Those are going to be, the values that cap x could be would be a 0, 1, 2, or 3. So that's the support of that random variable. And now the probabilities I need to calculate are conditional probabilities. And remember, for conditional probabilities, I'm going to need the joint probability. The conditional probability is going to be I'm going to need the marginal probability of 0.25 that I put in there. That's the marginal probability that cap y is equal to 0. And so the conditional probabilities are the joint probabilities divided by the marginal probability. So I don't put in for the probabilities. I'm looking along the row where cap y is equal to 0, and the probabilities I don't put in as a 0.12, 0.06, 0.05, and 0.02. I put in the probabilities 0.12 divided by 0.25, which is a 0.48, 0.06 divided by 0.25, which is 0.24, 0.05 divided by 0.25, which is 0.2, and then a 0.02 divided by 0.25, which is 0.08. So those are the probabilities that I get, and I want to make a comparison between the marginal distribution for cap x and the conditional distribution of cap x given that cap y is equal to 0. Notice that although the support for those random variables is the same, both random variables are going to be either a 0, 1, 2, or 3, the probabilities are different, and so those are different distributions. And being different distributions, it's telling me that the cap x random variable and the cap y random variable are dependent random variables. If you look back in the video on independent random variables, you'll see that if they were independent, I'd have the exact same distributions there, and I don't have the exact same distributions. The probabilities are different there. There's an easier way to show that these are dependent random variables, and I'll come back to that later in the video. However, I just wanted to make that observation. Remind you, in this particular problem, we're looking for the variance of this random variable, cap x, given that cap y is equal to 0. And so that's why I went through this process of filling out the table now, because the variance of any random variable is just its second moment minus the square of the first moment. Now, the first moment of this random variable is the sum product of the table, values in the table there, the values or the columns in red. For the second moment, then, I need to square the values first and then take the sum product. So square the values and then take the sum product, and I'll get as a second moment a 1.76. And then the variance of this random variable, this conditional distribution, would be, what is this, a 0.9856 is what I get when I take the second moment and then subtract off the square of the first moment. So again, that's how I would do the problem. I've seen this as a sample question. Somewhere in the sample questions, I saw a problem like this. And so that's how I would calculate the variance of a conditional distribution in this type situation. Okay, I want to change the joint distribution table. I want to look at another example where I change the joint distribution table, and I'll explain why in just a second. So let's use this as our joint distribution. Let's assume that we have this joint distribution table now. Let me fill in the marginal probabilities, and again, the marginal probabilities give rise to the marginal distribution. Those are just the probabilities that you're going to use in the distribution here, the marginal distribution. And what I want to observe here is that in this case, I have independent random variables. Now, the way that I would show that these are independent random variables is by showing that each of the joint probabilities is the product of the corresponding marginal probabilities. So, for example, let me just do one case as an example. If you'll take the 0.6, that's the marginal probability that cap y is 1, and the 0.25, which is the marginal probability that cap x is 1, and you multiply those together, you do get a 0.15. 0.6 times 0.25 is 0.15. And so if you'll do that for all the different arrangements of cap x and cap y, if you'll do that for all the different arrangements, you'll see that in every case, the value in the joint table is equal to the product of their marginal probabilities. And that tells me that I have independent random variables. If I'll go back to the table that I was using before, so this is the joint distribution table from the previous, up until now, until I just changed it. If I look at just the first value in the table, the 0.12, the 0.12 is not equal to a 0.3 times a 0.25. And so right away I know that these are not independent random variables. They're dependent. The cap x and the cap y are dependent because the product of the marginal probabilities does not give me the corresponding joint probability. But again, in the example that I've changed it to here, now I have independent random variables. Cap x and cap y are independent random variables. Let me put in the marginal marginal expected values here. The expected value cap x is 1.05 and the expected value cap y is 1.4. And what I want to do now is I want to look at, once again, the product of an cap x times a cap y. And when I do that, I'll leave it to you to show that that the table is, I filled in the values of the table correctly. I know that I did, and I'll show you why in just a second. But if I take the expected value of cap x times cap y now, I would get a 1.47. And the observation I want to make now is that the 1.47 is equal to the 1.05 times 1.4, which is the product of the expected values of cap x and cap y, respectively. In other words, this is a situation where the expected value of the product is equal to the product of the expected values. And this will always happen in the case that you have independent random variables. So because cap x and cap y are independent, you will get the expected value of the product is the product of the expected values of cap x and cap y. Very important fact that we're going to use throughout the next few videos, that if because of independence, the expected value of the product of cap x and cap y is equal to the product of the expectations of cap x and cap y. I can actually go a little bit further, and let me illustrate that with another example. Instead of a product of cap x times cap y, let's say I have a cap x that's squared times a cap y that's cubed. And so I'm going to leave it to you to show that the table becomes this. And I'll give you, I don't have a slide for this, but I'll just give you an example. For instance, if cap x is 1 and cap y is 2, I'm looking at the middle row in the table and the last column in the joint distribution table. Cap x is 1 and cap y is 2. Then the value of cap x squared times cap y cubed would be 8. And so if you look at 8 in the table below, you'll see that comes with a probability of 0.1, which is again corresponding where cap x is equal to a 1 and cap y is equal to a 2. 1 squared times 2 cubed is the 8. Okay, so now fill in the rest of the table that way, and I'll leave it to you to show that the expectation of this random variable is a 7.03 when I take a sum product. I know I did the arithmetic right. Again, I'll show you why in just a second. Notice that, so I got the expectation of the x squared times y cubed. If I just look at the expectation of x squared, now that has to do with the marginal distribution of cap x. So I'm looking at the second moment of cap x. I get a 1.85 in this case. Square the values of x and then take the sum product, and I get a 1.85. And likewise, the expected value cap y, I get a 3.8. And notice that the 7.03 is a 1.85 times a 3.8. In other words, what I showed here is that the expected value of cap x squared times cap y cubed is the product of the expected value cap x squared times the expected value cap y cubed. And that's always going to happen when you have these independent random variables. Well, let me explain what's always going to happen. When the expression that you're taking the expected value of can be factored as a product, where the first factor in the product has just x's, and the second factor in the product just has just y's, then you can just take the expected value of the product will be the product of the expected values. It might sound that might be confusing to you, so let me show you one more example of what I mean by that. Let's say that again, this all depends on the fact that the random variables are independent. But let's say now I'm looking at the expected value of a random variable that's defined as cap x times cap y plus a cap y. Notice that in the expression that I'm taking the expected value of, I can factor out a cap y, and I get now I have an expression that I'm taking the expected value of that's been factored. One factor just has y's in it, and the other factor just has x's in it. And what I'm saying is that now I could write that as the expected value of cap y. I could write that now as the product of the expected value of the factors, the expected value cap y and the expected value cap x plus 1. Of course, the expected value cap y is written right there, and the expected value cap x plus 1 will be one more than the expected value cap x, which is which will be 2.05, and then the product will be a 2.87. So that's what I would get as an expected value of a cap x times cap y plus cap y. Again, depends on the fact that I have independent random variables. So let me make one more observation here. I have independent random variables, and I know that when I have independent random variables, that the expected value of the product of x and y is equal to the product of the expected values of cap x and cap y. The point that I want to make now is that the reverse implication is not true. And so the converse is not true. In order to show you that it's not true, from a logic standpoint, what I need to find is an example where the expected value of cap x times cap y is equal to the product, but that cap x and cap y are not independent. They're dependent. And so here's my example then. This is my joint distribution table. Let's fill in the marginal probabilities, and you'll see that just when I fill in the marginal probabilities, it's very easy to see that these are not independent random variables. If you look at the first probability in the table, that probability in blue that I've highlighted in blue, notice that it's not equal to the product of the corresponding marginal probabilities, which would be both 1/3. And so I do not have independence here. These are dependent random variables. Now let's look at the marginal distributions of cap x and cap y. So that's, again, I've got the marginal probabilities. I just use those marginal probabilities to create a table, and that's what the marginal distribution is. And then I could find, I see that the expected values of cap x and cap y are 0 and 2/3 respectively. And now if I look at the product of cap x times cap y, the values that could be would be either a -1, a 0, or 1/3. I'm going to leave it to you to fill in the details of the table here. It's not very hard to see that, for instance, the only way that cap x times cap y could be a -1 would be if cap x is a -1 and cap y is a 1. And that comes with probability of 1/3. So fill in I'll leave it to you again to verify the table. Notice that the expected value of the product here, when I take the sum product there, I get 0. And so and then notice that the expected value cap x times the expected value cap y is also 0. So I get that the expected value of the product is the product of the expected values, but in this case, I got dependent random variables. So the implication at the very top then just goes one direction. Very, very important implication that's going to show up in a lot of problems, later, throughout your studying. For all the exams actually. But the converse of the implication is not true. So, okay, well that does it for this video, and I'll see you in the next one.